All right, this is CS50, Harvard University's introduction to the intellectual enterprises of computer science and the art of programming. And ordinarily, we would all be here on campus in beautiful Sanders Theater together. This, of course, is a little bit different this year for more than one reason. But we're here instead in the Loeb Drama Center at Harvard University. Thanks to our friends in collaboration with the American Repertory Theater, we have this new space, including even such amenities as a prop shop in back, where we've been working with an amazingly talented team over the course of the summer to prepare for this semester and CS50. And so I dare say we'll have some new and improved demonstrations along the way. So our thanks to our host, the American Repertory Theater. Now, we wanted to evoke memories, at least, or some imagery of the campus itself, particularly for the many of you who could not be here in person this semester. And so we went into the Harvard archives, where among their collections was this watercolor painting painted by a Harvard graduate student over 200 years ago in the year 1794, Jonathan Fisher, who sat in what is now Harvard Square looking in on some of the earliest buildings of Harvard's campus. And thanks to technology, we took what is a relatively small watercolor that this graduate student painted some 200 years ago, and now adorns the stage here in the Loeb Drama Center. So if unfamiliar, we have Holden Chapel here at left, Hollis Hall to its right, which is one of the undergraduate dormitories in Harvard Yard, Harvard Hall, which is one of the classroom buildings on campus, and then Massachusetts Hall, where both first years and Harvard's president live and work respectively. So welcome then to CS50, and I can say that not quite as long ago, but nonetheless feels rather long ago. Some 20 years ago, did I take the same class? But as you know, I myself had some trepidation when it came to studying CS50, when it came to studying computer science, because it was a very unfamiliar field. I had followed a path when I got to college of sticking within my comfort zone, studying government early on, thinking I would major or concentrate in government. And it wasn't until I got up the nerve to shop, that is, sit in on this class CS50, that I realized that homework can actually be fun. And I found that computer science and CS50 is not about programming per se, even though that's how many of us perceive it in high school, whether it's us or our classmates taking the class, but it really is about problem solving. And as such, it's so very applicable not only to computer science and the engineering fields, but really to the arts, humanities, social sciences, and beyond. And so if you're feeling a little uncomfortable with the idea of taking a class like CS50, know that most every year, nearly 2/3 of the students who take CS50 have never taken a computer science course before. So if you look up, down, left, right now, odds are more than many of the classmates joining you here today are in a very similar position. You're indeed in very good company. And what's ultimately important in CS52, we emphasize, as in the syllabus, that what ultimately matters in this course is not so much where you end up relative to your classmates, but where you end up relative to yourself when you began. Indeed, taking into account where you currently are, perhaps with no prior background, and considering where you will be in just 3 or so months is ultimately meant to be the measure of your own success. And so toward that end, we'll start off this class programming a little something from yesteryear, an image here of Super Mario Brothers and the pyramid that the character has to ascend. We'll recreate a portion of this game, albeit using text, otherwise known as ASCII art, but we'll do that in just the course's second or so week. So this will be among the first programs you write, and then fast forward just several problem sets or programming assignments later, or several weeks later too, and you'll be building what we call CS50 Finance, a web application of your very own that runs on the internet, pulling down nearly real-time stock quotes from a third-party service, allowing your own users to log in and register to buy and sell stocks, so to speak, using virtual currency. So over the course of the classes, several months, will you go truly from building a pyramid in Mario to building your very own web application and more, followed by the course's capstone experience, which will be your very own final project. But what exactly is computer science? What we thought we would do in this week 0, the very first week of the class, is consider exactly what it means to solve problems. And let me propose that this is computer science. This is problem solving. You have some input, which is the problem you care about, that you want to solve, and you care about the solution to that problem, which is the so-called output. And in between that input and output is this black box of sorts, inside of which is sort of the magic that happens, the magic that you'll eventually be able to harness and compel computers to solve problems for you. Inside of that black box ultimately is going to be the code that you write. But for us to begin doing that, we all kind of need to agree on how we're going to represent these inputs and outputs. We all kind of have to speak a common language, so to speak. And so we need to agree how these inputs are going to be represented. So how might we typically represent information? Well, maybe the simplest thing to do at the very first class, whether we're online or in person, is to take attendance or to count the number of people in the room. And so you might do this old school style on your hand, so as to represent every person in a room with just a finger raised on your hand. So how we might represent information boils down to very simple digits on your hand. Of course, you can't count very high with just this hand, but there's actually a fancy word for what we're doing old school here, and that's unary notation. Uno implying one, or one finger being up or down. And so you can count, it would seem, as high as 5. And of course, if I bring in a second hand, I can go as high as 10, and then things get a little more difficult. But it's a system for representing information, and it's fairly universal, certainly when we're all quite young. But you and I tend to use a more useful system, not just digits on the hand, but other sorts of digits, namely the decimal digits that you and I know. So the numbers that are otherwise more technically called base 10, and that's just a fancy way of describing the fact that there's 10 digits that you and I as humans really tend to use typically. And those digits, of course, are 0 through 9. And using these several digits, we can compose numbers like 0 through 9, but also 10 and 11 and 12 and as high up as we want to go by using multiple digits still. But computers don't really speak the same language as us. They're, in some sense, much simpler than we humans, even though they seem so complicated or so sophisticated and certainly so fast. At the end of the day, these are all human-made devices, and they're relatively simple at their core. In fact, even if you don't quite know what you're saying, but you've at least heard this to be the case, what language do you understand computers to speak? What language do computers speak, if not the system that you and I use of zeros through nines or decimal? Ryan, could we see who might answer this? What system do computers use, so far as you've heard, whether or not you've taken a CS class before? Keith, can we go to you first?
Yeah, the computers use binary.
Binary. And can you elaborate a little bit? What do you mean by binary?
It's zeros and ones. So like while we use 0 through 9 for base 10, it uses 0 through 1 for base 2.
Yeah, exactly. So computers use the so-called binary system, bi implying 2, and they indeed only use, as Keith notes, 0 and 1, 2 digits. So on the one hand, this is actually pretty encouraging because, wow, this is actually a pretty simple system if we're only using two of these digits. But of course, if you only have 2 digits, how are we going to represent the number 2 or 3 or 4 or any much larger number? It would almost seem like a step backwards. But it isn't actually. And it turns out that this so-called system, or base 2 because there's 2 digits in the vocabulary, otherwise known, as Keith says, as binary, uses just zeros and ones. And it turns out there's other nomenclature here we can toss out. These zeros and ones are otherwise known as bits. And bits actually derive from just 2 words, binary digits. Binary implying 2 possibilities, digits just being symbols on the screen. So binary digits are otherwise known as bits. And computers speak binary using these things called bits. But what does that mean, and why is it the case? Like, why didn't they invent computers decades ago that just use 0 through 9 rather than come up with a whole new system for us to think about, let alone talk about? Well, at the end of the day, computers are using what is their input? Really just electricity, right? Probably the only thing all of us do every day or every couple of days with our laptop or desktop or phone is either make sure it's still plugged in, or 2, plug it in so as to charge it. So the only physical input to our devices these days is electricity in some form. And we don't have to get into the nuances of what electricity is, but I think it's about electrons flowing into the device so as to charge it. So it suffices for our purposes to know that there's some physical input to the device, these computers and phones that we use. But that's it. And so if we harness this electricity, maybe we can start to represent information with it. For instance, here is a light bulb, this old ghost light in the theater here that's currently off. But it has the ability to turn on. We just need to plug it in or throw on a switch. And if that's the case, what's really quite compelling about the metaphor of using lights is that right now this light bulb is currently off. But as soon as I allow electricity to flow, as by plugging it in or maybe throwing a switch, now it's, of course, on. And if I unplug it or throw the switch again, it's off. Or if I plug it back in, it's on. And the implication of this very simple idea is that we can take a physical device like a single light bulb, and by plugging it in or unplugging it, we can represent information. What did I just do? I represented the light bulb being off or on, but we can just call off and on something else. We can call them zeros and ones. And so this really is the germ of an idea that gave us computers, and with it, their use of the binary system. If at the end of the day, all they have as physical input is electricity, well, let's just use that to harness and keep track of information. Let's store a little bit of electricity when we want to represent a 1, and let's let go of that electricity in some sense when we want to represent a 0 instead. And so because the input to computers is so simple, thus gives us these zeros and ones that we now use, but we seem to have created a problem for ourselves. If we only have one light bulb or one switch, if it's off, it might be a 0. If it's on, it might be a 1. But how do I count higher than 1? That problem still fundamentally remains. Well, I could, of course, use more light bulbs. So let me ask this. If we were to use 3 light bulbs, how high could we count? So with 1 light bulb, we can count from 0 to 1, 2 possibilities. But with 3 light bulbs, how high could we count? Well, let me go ahead and ask this question here on the screen. In just a moment, you'll see on your side this particular question via which you can respond on your device. How high can you count with 3 light bulbs? So instead of 1, I give you 3, each of which can be on or off. How high can we perhaps count? So you'll see on the screen here, the answers coming in. We have a lot of folks thinking 60+% that it's 8 is the highest you can count. A lot of you think it's 7, and some of you also think it might be 3 or 2. So that's actually an interesting range of answers, and let's see what might actually be the case. Well, let me cut back over to 3 actual light bulbs here, all of which are off. And most naively, I think if we were to turn these light bulbs on, if they currently represent 0, obviously I could turn 1 on, and we could call it 1. Then I could turn the second one on and call it 2. Turn on the third one, and now with all 3 on, we could say now we're representing 3. But we're not really being clever enough just yet if we're only counting as high as 3, because I'm just turning them on in this story left to right. But what if we were a little more clever? Maybe we turned them on right to left, or maybe we kind of permuted them in different directions. That is, we took into account not just how many bulbs are on or how many fingers are in the air, but rather the pattern of on and off light bulbs that we've created. So let's just count this up. So let me somewhat systematically turn some of these bulbs on here, albeit virtually. Here might be 1. Here might be 2. Here might be 3. But then we're kind of done with that story. So how might we do it a little better? Well, let's start again at 0. Here might be 1. Why don't we call this 2? Why don't we call this 3? Why don't we call this 4? Call this 5, this 6, and this 7. Now, it's fine if you didn't quite see what pattern I was following, but take my word for it that that was a unique pattern of light bulbs 8 total times. I started it off, 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 and I ended it on, on. But along the way, there were indeed 8. But how high can I count? Well, it kind of depends on what number you start counting from. And just as we thus far have been doing, computer scientists do all the time. Computer scientists, and in turn computer programs, typically start counting from 0 just because it makes sense, because when everything is off, you might as well call that 0. So if we start counting at 0 and we have 8 possible patterns that we just saw pictorially, well, that would allow us to count as high as 7. So from 0 to 7, so 7 is the highest we can count with 3 light bulbs. So those of you who proposed that 7 was the answer, 36% of you were indeed correct. 57% of you who said 8 are correct if you assume we start counting at 1, and that's fine, but at least in the computing world now, will generally, by convention, start counting from 0. But you are correct to say that there's 8 such possibilities. All right, well, this is all fine and good to represent things with patterns of light bulbs. But how do we actually now get to the zeros and ones that a computer is actually using? Because what's inside of a computer at the end of the day are not light bulbs, but tiny, tiny little switches, millions of little switches that can either be on or 1 or off or 0. Those switches happen to be called transistors. And these days, computers do have millions of these things that can be on and off in different patterns. So if you have the ability to turn on and off all of these switches, well, what can we all agree on representation when it comes to using those switches? How will we represent information with them? Well, wonderfully, we don't really need to think very hard or go past our very comfortable roots as kids if we consider for a moment not just 0 and 1, but the whole decimal system, 0 through 9, that you and I all started our day with today. How does that system work? Well, here on the screen is 1, 2, 3. So yes, you're probably thinking that's 123, but not quite. All I've shown on the screen is a pattern of symbols, 1, 2, 3, or 3 digits. And all of us probably are instinctively just saying, obviously, it's 123. But it's probably been years since you considered why it is 123. Well, let's consider what each of these digits or symbols represents. If you're like me, you grew up learning that the rightmost digit is the ones place, the middle is the tens place, the left one is the hundreds place. And so how do we get from these 3 symbols or digits, 1, 2, 3, to the mathematical idea we know as 123? Well, all of us instantaneously these days did 100 times 1 plus 10 times 2 plus 1 times 3, which of course is just 100 plus 20 plus 3, or the mathematical value we all know as 123. So a bit of a circular argument, but just to remind us how we got from 123 to 123. Well, it turns out that in the world of computers, the system they use is exactly fundamentally the same. The only difference is that computers only have access to zeros and ones, not zeros through nines. So if we consider now in the abstract just 3 possible digits represented here, let's consider for a moment why those columns or places were 1, 10, and 100, and so forth. Well, why was that the case? Well, there was a pattern, in fact, and it just has to do with exponents or powers. So the rightmost column, technically, if we really get into the weeds, is 10 to the 0th power, which, if you recall, just means 1. 10 to the 1st power, which is just 10. And 10 to the 2nd power, or 10 squared, is 100. But what's interesting about representing it in this way is that it jumps out that 10 is involved. There's 10 digits, 0 through 9. So the columns are using this base of 10. So you can perhaps now get even ahead of me here by considering, well, if in the binary system that computers use, you only have 2 digits, zeros and ones, odds are the only thing that's going to change is the meaning of these columns. Now we have the ones place still, because 2 to the 0 is 1, but then we have 2 to the 1st, 2 to the 2nd, and so forth. And of course, if we just do out that math, in the world of binary that computers use, we have the ones place, twos place, fours place, and so forth. And now we're good to go. Even though we have to now think in a different base system, now we can start counting more properly. And now we can move away from the metaphor of light bulbs and consider that if all of those light bulbs are off, we're again just going to start thinking of those things as zeros. So that would be a pattern of symbols or digits that's 0, 0, 0 in binary. But in our human world, the mental math you would probably do now instantaneously after today would be, well, that's obviously 4 times 0 plus 2 times 0 plus 1 times 0, or of course 0 in decimal. But how does a computer represent the number 1, for instance? Well, it's just going to change that rightmost bit from a 0 to a 1. Or, more metaphorically, it's going to turn that switch on and illuminate that rightmost light bulb, just like I did earlier. How do I represent 2? It's going to be 0, 1, 0 in binary. How do I represent 3? This is where we're about to differ. Now I'm putting on 2 of those switches because I need something in the 2's place and the 1's place to give me mathematically 3. Next, if we go ahead and choose count up to 4, that's going to be 1, 0, 0. If I want to count up to 5, that's going to be 1, 0, 1. 6 is going to be 1, 1, 0. And finally, the number 7 is going to be 1, 1, 1. So it would seem that using 3 bits, each of which can be a 0 or 1, yes, you can permute them in 8 different ways. 2 possibilities for the first, times 2 for the second, times 2 for the third gives us 8. But as per this math and the intuition of starting counting from 0, we can only count up as high as 7 in total. Well, let's go ahead and actually take this out for a spin. When we don't have just, say, let's say, 1 light bulb or 3 light bulbs, we have actually the fortune of having like a whole stage worth of light bulbs. 64 light bulbs adorn the stage here. And you know what, Sumner, could we go ahead and put up a random number on the screen here? All right, so if you can see these light bulbs from your perspective, we have 8 light bulbs plus another bunch of them off, and all the others are off. So let's go ahead and ask a question then. If these light bulbs now represent not just 1 light bulb or 2 or 3, but several more, in this case at least 6 light bulbs, what value do we actually get? Well, let me go ahead and put a question on the screen here, which should pop up on yours in just a moment. And you should see now on your end this same question put in binary terms. What number in decimal does binary number 110010 represent? What decimal number does binary number 110010 represent from left to right? So here we have an overwhelming response. 50 is indeed the correct answer. Now, why is that? Well, if I go over to the physical light bulbs here, let's just consider for a moment what the pattern actually is. This here is the 1's place, the 2's place, 4, 8, 16, 32. And we could keep going, but it's not going to matter because they're all off. So we have 32 plus 16 plus 2, which indeed gives us the number you and I know in decimal as 50. And just imagine how high we could count with all of the other light bulbs as well. All right, so we started with the story with electricity. We then moved on to numbers and representing things either in decimal or in binary. But we've kind of painted ourselves into a corner, because if we only have at our disposal switches, or the metaphorical light bulbs, which we can think of as 0s and 1s, it would seem that the only things computers can do is compute, that is, behave as calculators. And in fact, early on, that's exactly what computers were designed to do, was really facilitate mathematical calculations that were otherwise quite tedious or impossible for humans. But of course, what you and I are using right now, what we use every day on our phones and our laptops and desktops, is much more sophisticated. So let's consider, how could a computer represent not just numbers, but letters of the alphabet? Brian, could we call on someone for this one? If you'd like to raise your virtual hand, how could a computer go about representing letters of an alphabet like English if, again, all we have at our disposal is switches?
We can assign the numbers that we're getting from binary to specific letters in the alphabet.
Yeah, we can assign the specific numbers in binary to letters of the alphabet. That's pretty much our only option, it would seem. If we only have the ability to permute these switches or light bulbs or bits, well, we just all have to agree how to represent letters in the same way. Now, maybe the simplest way for us to do this would be, you know what, let's just all agree that a capital A is going to be the number 1. So you turn on 1 light bulb, or represent the binary number 1. Well, how about for B, we could use the number 2. For C, we could use the number, the number 3. D could be 4, and so forth. We all just have to agree to number the letters in that way. But it turns out humans did exactly that, but a little bit differently years ago. They decided, for reasons that we won't get into just now, that actually the capital letter A is actually going to be represented by the decimal number you and I know as 65. Now, in bitwise form, that's going to look like this. So this is the pattern of bits that a computer would use to represent the decimal number we now know as 65. And now what the computer is going to do is just be mindful of what type of program you're using. So yes, if you're using a calculator, or maybe using something like Excel to crunch numbers, well, in that context, when running software like a calculator or a spreadsheet program doing numerical analysis, the program is going to see inside of the computer's hardware the pattern of switches that represents the decimal number 65. And because it's in the context of a calculator or spreadsheet, what you, the human, might see on the screen is literally the decimal number 65. But if you and I are using text messaging or email or any number of social media apps where we're communicating not numerically, but in letters, say English letters, in that context, your computer is going to be smart enough to know, well, that same pattern of bits that represents 65 in the context of a text message or in an email or the like actually represents the capital letter A. So the pattern is the same, the representation is the same, but the context is what differs. And the system that humans came up with years ago that maps 65 to A, 66 to B, 67 to C is called ASCII, the American Standard Code for Information Interchange. And that just means that there is a well-defined mapping that a bunch of humans decades ago decided on in order to map letters of the alphabet, English in this case, to numbers, starting with 65. And there's a whole mapping, too, for punctuation, for lowercase letters, and the like. So given that, suppose that you did receive a text message containing a pattern of bits, or really just a sequence of decimal numbers that happen to be this: 72, 73, 33. Suppose that you received a text message containing these patterns of numbers: 72, 73, 33. What message might you have just received? Let me go ahead and pull up the abbreviated chart here to consider exactly what message you've received. 72, 73, 33. And Sumner, could we go ahead and throw this same three-letter word on the lights? If you'd like to see it in bitwise form, so to speak, will appear here on these light bulbs now as well. What pattern does this represent? Lanham, can we go to you?
That would be high with an exclamation point, correct?
Yeah, so it's indeed high with an exclamation point, and it's probably pretty easy now in retrospect to glean that, yes, the 72 and the 73 were H and I respectively. But Lanham also noted the exclamation point, which it isn't in this chart, but per the ... dots, there is a well-defined mapping for all of the letters of the alphabet that we might care about. And so high is perhaps more obvious than the other. That 33, we need a bigger chart. And so if you actually go on your computers now to ASCIIchart.com, ASCIIchart.com, you'll see a little something like this, though you can also just Google ASCII in general and get copies of the same chart. You'll see here that H is indeed 72, I is indeed 73, but if we look to the left, 33 is apparently an exclamation mark. And you would only know that by having looked it up or just having committed it to memory, but the computers you and I use and the phones you and I use just know this intrinsically. That's indeed how they're programmed. But it turns out, too, that we should consider just how many zeros and ones we're using now to represent the 72, the 73, and the 33. So let's look for one last time at the binary representation, which as per the light bulbs are these patterns of bits here. So when you receive a text message from a friend saying, hi, HI exclamation point in all caps, you're technically receiving a pattern of bits, some kind of frequency if it's wireless, that represents this pattern of bits. And typically computers these days use 8 bits to represent each of those characters. When ASCII first came out, they typically used 7 for efficiency reasons because space was expensive back then. But here we used 8, and indeed that's now the norm when it comes to representing characters in multiples of 8. So we have 8 bits here, 8 bits here, 8 bits here, which means to receive the message hi, you are sending or receiving 24 bits total. Now, frankly, bits are not a very useful unit of measure typically because they're so small, just a 0 or a 1. But each of these patterns of 8 bits actually have a vocabulary word, if you will, which is bytes. And odds are all of us have used this term in some context, but generally in the context of megabytes or even gigabytes. Indeed, when you talk about the sizes of your files these days, you're speaking in bytes in some form, either million or billion bytes. But each of those bytes, quite simply, is a pattern of 8 zeros and ones. So in fact, if we have as many as 64 bulbs at our disposal, that's 64 divided by 8. That's 8 characters. So it would seem we could spell on this stage even an 8-letter word. If Sumner, we could put up a random 8-letter word that we'll keep up now. Can you now spell from left to right, your left to your right, an 8-letter word using the system known as ASCII? But of course, we're being a little bit biased here, as ASCII is the American Standard Code for Information Interchange. And on a typical US English keyboard, there's more characters certainly than uppercase letters like A through H and I. There's also some punctuation and some numbers, but there's also quite a bit missing as well. And any of you who are elsewhere in the world, odds are would find using a keyboard like this especially limiting especially limiting or frustrating. Why is that? What seems to be missing from ASCII? What seems to be missing from ASCII? Well, let me ask this one other question here. If we do use ASCII and we therefore give ourselves 8 bits or 1 byte, how many different characters could we potentially actually display, actually represent? So on your screen, you should see this question now. How many symbols can you represent with 8 bits? How many symbols can you represent with 8 bits? And this speaks to, really, at the end of the day, how many letters of the alphabet, plus punctuation, plus uppercase and lowercase, can ASCII, or really can computers, support? Well, it looks like 72% or so of you think that the answer is 256. And it is indeed the case that you can represent 256 possibilities. Why? You can actually do out the math. If you've got 8 bits, each of which can be a 0 or a 1, that means you have 2 possibilities for the first, times 2 possibilities for the second, times 2, times 2, times 2. That happens to be 2 to the 8th, or 256. It's fine if that's not immediately obvious, but if you do have 8 bits, each of which can be one of 2 values, you can come up with 256 possibilities. Those of you who chimed in to say that the answer is 255, in this case are wrong only because now we're talking about the total number of patterns, which is indeed 256. But the highest value we could represent with 8 bits or 8 light bulbs, it would seem to be indeed 255. And that's because of all of the different patterns we can permute. But let me open the question to the audience now. Why might a US English keyboard be especially limiting? And in turn, why is ASCII really not quite appropriate when it comes to representing human language, even though this is what computers began with years ago? What is missing from ASCII? Why might 256 total possibilities not be sufficient? Kevin, can we go to you?
Sure. I mean, for one thing, missing a lot of the accents that are in other languages. But if you just consider like Asian languages, there are a lot more than 256 characters.
Exactly. So not only are we missing accented characters that you might need in some languages, we're also missing the characters that you might need in Asian languages, in languages like Arabic and the like. There are way more symbols that we humans use to communicate in print and electronically than 256. English we can get away with fitting into this keyboard, but not once we introduce things like these characters, let alone other symbols as well. And it turns out there's other things we humans like to say these days and express using characters that have come into vogue, which is namely these things. Odds are probably sometime today you have sent or received one of these things here, otherwise known as an emoji. Now, even though these emojis look like pictures, they look like images, and they are technically, the way they're implemented in computers is actually as patterns of zeros and ones. These are actually just characters in an alphabet, the emoji alphabet, which is to say there's some pattern of zeros and ones that represents each one of these faces and the many other emojis that nowadays exist. And this is because the world has transitioned over the years from ASCII, which only used 7 and in some sense 8 bits total to represent all possible characters, to using either 8 or 16 or 24 or even 32 bits. Nowadays, there's a system called Unicode, which humans have come up with that support not only English, but also all of the human languages is the aspirational goal, both written and written in print or electronically is the goal. And in addition to that, this is to say we can represent things like this. So this is the so-called face with tears of joy. And this face of tears of joy, as of last year, was the most popular emoji sent via text messages, emails, social media, and the like. But at the end of the day, all you're receiving is like a key on a keyboard. So in fact, you wouldn't know it to look at it. But in fact, the decimal number representing this face with tears of joy happens to be 128,514. So to Kevin's point, to represent not only certain human languages, but certainly these emojis, we need way more than 256 characters. So we can use not just 8 bits, but 16 or 24 or 32. That's a huge amount of possibilities now. In fact, now to really take the fun out of these things, if you receive that face with tears of joy or send it, you're technically just sending a pattern of bits that looks like this. That's all that's going on underneath the hood every time you use these things. All right, so we started again with electricity, we then represented numbers. Now we have the ability to represent letters and even emotions in the form of emojis. What else is there out there? Well, the emojis themselves, of course, at least the ones we've looked at, are pictorial in nature. And so that invites the question, well, how does a computer represent things like color? Like that face with tears of joy had a lot of yellow in it. So how is yellow, or any color for that matter, represented in a computer? Well, let me ask the audience again. If all you have at your disposal is bits, zeros and ones, and we just, as humans, need to agree how to represent colors, what might be one possibility? It doesn't need to be the answer, but what might your own instinct be if designing this for the first time yourself? How might a computer represent colors now? Yasmin, what do you think?
You would like assign numbers to different colors and shades and just use the same system?
Yeah, exactly. Perfect instincts. You would just assign numbers to the different colors, and we all just have to agree on what that mapping is actually going to be. So it turns out there's different ways to do this. And if any of you are artistic and use Photoshop or the like digitally, you're probably familiar with acronyms like RGB, red, green, blue. But there are other acronyms and other ways to implement Yasmin's idea where we just somehow map zeros and ones to actual colors. Well, RGB just happens to represent red, green, and blue. And this is a system humans came up with years ago that says, you know what? We can actually get every color of the rainbow by mixing together some amount of red and green and blue light, essentially. So that just invites the question, well, how do we represent the amount of red? How do we represent the amount of green? And how do we represent the amount of blue? And we have, as Yasmin says, bits at our disposal. So we just have to decide how to do this. So suppose we receive a pattern of bits that's 72, 73, 33 again. But this time it's not in an email. It's not in a text message. It's in the context of a file that I've opened in Photoshop.